Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll look at some of the common pitfalls when using Scikit-learn. That is to say, what are the things you should be doing and what are the things you should not be doing. These are the items: inconsistent processing, data leakage, and controlling randomness. The very first one, in case of inconsistent processing, what we want to do is, if there are certain number of steps that we use or follow while training, we want to make sure we follow the same steps while working on subsequent data such as test data. In this case, these steps are clean, reduce, expand, and generate features. So we want to use exact same steps on the test data as well. Here is an example. Let's say we have this data set with data X and Y, which created using the make underscore regression, and we split it into train and test set. Now, in this case, if we perform the standard scalar on the train set and we immediately use the test data to perform the prediction, the test data that is not yet transformed, you get a very low accuracy score of 60. Mean squared error, we get a mean squared error of 62.8, and that that is not correct, because here in this case the data that we are using in case of X test is not transformed or is not scaled as the X train was. Now if we perform the transformation on the X test and then look at the mean squared error, then we get a mean squared error that is 0.9. So as you can see, this was a pretty high mean squared error, but after transforming the X test data, same way we get a lower mean squared error value. So that is something to remember. And Scikit-learn does provide the pipeline, make pipeline method. So you can create a pipeline, and within the pipeline will take care that the test data and the train data both need to be normalized correctly. So that's another way to perform, to use the same steps that were used for training in the test or prediction part. Now, data leakage, you probably heard this word before. What it means is, at least this is my understanding, is that while training a model, if there is any information from the test set that gets into the train set, then the model already has the information from the test set, and that's the flow of information from the test to train is called data leakage. And that is not advisable, because the model would be built on the data that already exists in the test set. So if a new data set comes in, then the model may or may not be able to fit the new data set well. In competitions, however, the data leakage again is important. So there, if there is data leakage, it's posted in forums, and you want to make sure that your modeling process or modeling steps takes into account what type of data leakage is there. And as a general rule of thumb, you don't never want to call a fit on the test data, and that could be fit from preprocessing. And the reason is simple, that if you perform a fit on the test data, then you are leaking data into the model building process. Here is an example. Again, we have X and Y. These are the values. And then here we have X. We are selecting K is equal to 25 features. We're performing fit transform, and then using a gradient boost classifier to get the prediction. So we get a prediction in this case of 0.76. And in this case, the issue is that we have transformed the entire data set here before performing the train test split. So this line in orange, it should be such that it should be fit on the X train and then transform on an X train and transform on X test. So such as shown here. So we perform the split first, then perform the fit transform on X train, and then perform the transform on just the X test. And as you can see, the accuracy score, it was high here, 0.76, and that's likely because of the data leakage when we perform the fit transform before splitting the data set. In this case, we can use a pipeline. So after we have the X train and X test split out, then we can create a pipeline, and the pipeline can have the X select K best and the gradient boosting classifier. Then we can fit the pipeline to the X train and then use the pipeline to predict on the X test. So that takes care of the transformation automatically. And this should have been the same color as this, but I've colored it blue here for some reason. And again, the accuracy score is 0.46 as we saw earlier. And here we again can use the pipeline in crosswell score, and we get accuracy of 0.45 plus minus 0.07. So about the same range as what we had earlier. And again, as we talked earlier, always split the data into train and test sets before performing any pre-processing steps. So the test data should never be touched until the final model is ready. And never include the test data in when using fit or fit transform. So always perform the fit on the training data, and only transform could be applied on the test data. So a transform that was fit on the train set. So what happens is when we perform a fit, the coefficients are generated, and those coefficients from the train set can be used to perform the transformation of the test set during pre-processing. And the pipeline is very helpful, so it can minimize errors in this transformation step. So it's always advisable where possible to create a pipeline for pre-processing. So if any new data set comes in, it can flow through the pipeline and you have the result or prediction. Now moving on to controlling randomness, some of the classifiers or some of the estimators in Scikit-learn, they have inbuilt, they are inherently random. So to say, for example, random forest classifier, it creates random trees. And so in this case, the randomness of these objects is controlled by the random state parameter. Now the random state in some cases, in some estimators, is by default it's set to none. So you can change that and pass in either instance or an integer. So if an integer is passed, so let's say integers, if you pass in 0 as integer, then if you run the same line of code, it will give the same result. However, if you pass a random state instance, then you may get a different result each time you run the code, and it will become clear as we look through some examples. Here is an example where we create a variable RNG and supply it with np.random.randomState 0, and that is the RNG that we are using as an input to make classification here, and we are using that RNG as the input to the SGD classifier. So random_state is equal to RNG. Now when we run this sgd.fit and try to get the coefficients of the model, each time we run it, we get different coefficients. So here we have 2 runs and we see that the coefficients are different. and it means that we have a different model because the coefficients are different. So in such cases, you want to make note of this, that if you are running, if you are using an instance in case of random state, every time you run it, it may get initialized, uh, it may initialize the modeling process differently, and so you have different coefficients in each iteration. On the contrary, if you set that random state to an integer value, then you get exactly the same output. So that is something to keep in mind. So for example, if you are trying to uh, build a model, and if I'd suggest setting this to integer if you are expecting the same, if you need the same exact coefficient in each iteration, if you do some changes elsewhere in the code and you want to see how the accuracy changes, then it's better to have the same coefficients using the random state. As the coefficients won't be the same, but at least you know the random state is the same, and with that you know if the results were different because the changes elsewhere, or it very different due to the random initialization. Again, the usage of random state in cross validation splitting, if we use the instance of random state as shown here with k-fold, and each time we run the cv.split, we get different output, as we can see here. However, if we use an integer, then we get the exact same output that we can see here. Now, some of the common pitfalls when using the random state in case of estimators is that different random state type leads to different cross validation procedures, and here is an example of that. We have the data x and y, and then we have the random forest classifier. Here we set it to an integer 1 2 3, and here we get a score of 0.85 and so on. Now if we perform the same classification, and instead of passing an integer value, we now pass a random state instance. In that case, we get the output that is shown here. So the results are different in case the first result is different, and that is because when we are using the random state instance, the initialization would be different when the process of training is going on. Now, in case of cloning an estimator, again, if we use the instance, if we set the variable a to random forest classifier, and b is a clone of a, then a and b still would be different models, because even if they are trained on the same data, because we are using the random state instance here. Again, another example of common pitfall with cross validation splitting is, let's say we have a variable RNG set to the instance np.random.randomState, and we use that as an input to the random state with k-fold. So what this is going to do, each time we perform a k-fold split, it's going to result in different indices, and so a different set of uh, records would be assigned to each fold. And now if we are trying to perform if we have two different models, estimators, that we want to find a cross validation score on, then that particular random initialization would affect each of those estimators. So in this case, as the docs suggest here, that comparing directly comparing the performance of LDA estimator versus Gaussian Naive estimator on each fold would be a mistake, and that's because the splits on which the estimators are evaluated are different. And so to get reproducible results across multiple executions, what is suggested is that we want to remove all instances of random state is equal to none, and it is recommended that you declare a RNG variable at the top of the program and pass it down to any object that accepts a random state parameter. Keeping in mind some of the examples that we talked earlier, that instances where we cannot compare different models because the random initialization could lead to a different uh, records being assigned for training in each iteration. And here is an example where np.random.randomState, we have initialized it. Then we have the make classification, and this is the random estimator. We have random forest classifier, and we are performing the train test split again using the RNG, and then we perform the fit and get the score. So in this case, what we are doing is we are using the same RNG across the entire code until we get the score. Now, to look at the robustness of cross-validation results, there are two things to remember. One is that when you pass an integer, the estimator will use the same RNG on each fold. And so if the estimator performs well or bad as evaluated by CV, it might be just a matter of chance. So it is advisable to pass an instance to the cross-validation process to make it more robust. And this is again a suggestion by Scikit-learn docs towards the end of the documents, and it says we do not recommend setting the global numpy seed by calling np.random.seed 0. So they have explanation on this. I'm not going into that right here, but that is something to keep in mind. Instead, the suggestion is to use np.random.randomState. That was it then for this video. I hope in this video you learned some of the to do and not to do when using scikit-learn methods. We looked at random initializations, what can be effect of that during training. And then when we looked at inconsistencies, and one most important point to take away is that uh, always perform the split before doing any pre-processing. So you want to keep the test data separate aside, untouched until the final model is ready. And wherever possible, just use a pipeline so the test data can go through the same pipeline through which the trained data went, and thus you have consistency in creating the models. And that was it for this video. I hope to see you all in the new series, as this was the last video in the intermediate series, and I wish you good luck in using these methods that we have discussed, and I hope you enjoy creating prediction models and applying it on real world data set, toy data sets, answering questions. If you have any suggestions on any other topics that you'd like be discussed, please feel free to post them in the comment section below. Thank you.